All right, well, thank you. And again, Henrietta, thank you for having me and organizing and accommodating my travel or lack thereof. I did tell Henrietta that I would be more than happy to do the next talk in person. Hopefully next year. The way things are lining up. I also noted the last time I came out of Chicago, I got one of the last flights out of New York before everything shut down due to a blizzard. So it is what it is. So yeah, so tonight we're going to talk about building what I call a complex real-time data management application with Postgres. And this isn't really like a hypothetical exercise. This was actually based upon work I did at my previous company before I joined Crunchy Data. It's basically a simplified version of our calendar management system in it. As Henrietta said, when she exerted her executive authority to, demand this talk, I decided to look into doing this, with Postgres 14 and seeing, with the updated Postgres version, would there be any changes to it? In fact, there were some significant changes, which we'll talk about today. So I'm actually glad I got to update it. Let me just go through a little bit of the standard boilerplate about me. I work at a company called Crunchy Data. All we do is focus on Postgres. I run our platform engineering team, which basically focuses, primarily these days it's deploying Postgres on Kubernetes. We have software that makes it very easy. It's open source. Check out crunchydata/Postgres operator. I've been active in the Postgres community a pretty long time now. I'm on the core team. I typically work on things involving governance, advocacy, legal, essentially all the non-code aspects of the project. And I've been involved in various committees, conferences, et cetera. Probably can talk a lot about all those things. Crunchy Data. As I mentioned, Crunchy Data, all we do is Postgres. We believe open source is the enterprise solution. Everything we do is open source. We have a managed service called Crunchy Bridge. It's pretty cool. I actually almost did the demo on that tonight, but I opted to do the Kubernetes side of it. And yeah, we're like pretty much every tech company we are hiring, and we also do cool stuff. So this talk is promising to do a lot because you're going to see exactly what we're going to be covering, and to be like, great, how are we going to do this in a roughly 45 to 50 minutes? And the idea is that yeah, we're going to speed through some of these things. Like more of the idea is that we're going to talk about concepts and introduce them, and then I'm going to provide the code and the examples later so you can go through it on your own time. The idea is to inspire. The idea is to see here's all these like cool things you can do with Postgres that are coming in right out the box and integrating it with, let's say, a programming language like Python. And give some sense of how to do it. And then again, I'll make the code available so you can really dive into it. That's the only way we can get through this in 45 minutes. There is the 3-hour version of this talk where like we'll go through everything line by line by line, but we're not doing that today. So with this, what's the problem? What are we trying to solve? I don't necessarily like building tech for tech's sake. I like a tangible problem. The problem is, we are a user group organizer and we manage virtual rooms for our events. And there's a certain set of operating hours in which these virtual rooms can take place. And maybe it's like, arguably it's 24/7, but you need a moderator. And Henrietta being the moderator needs to sleep at some time. So we have to close the virtual rooms. And you can only have one booking in the virtual room at a time. We don't want to have 2 presentations going on at the same time. So it's a calendaring app. And the example I had was actually from PGConf EU 2018, where they had one, this was in person, but there are 3 tracks and there's a talk in each track at any given time. And look, lo and behold, I gave the same talk at that conference. So yeah, this makes sense. It's a simple calendar booking app. Like, okay, it doesn't seem too bad. There's some specifications that we need to know all the rooms that are available to book. When the rooms are available to be booked, which is basically the operating hours. And of course, when the rooms have been booked, like when they're unavailable, we also need to be fast. Like we can't just be sitting there waiting all day for these things to occur. And you think about that, and it's like, maybe this doesn't seem too hard on the surface, but I can tell you that when it gets to a certain scale, it actually gets quite hard to do all those things well at once, to be able to both like insert the data quickly and update the data, and basically read the data quickly. Like there's, it got to like this weird like push and pull trade-off. And basically, like, how did I discover this? For one thing, as I said in my previous job, I lived this. That's how I discovered it, the hard way in some ways. But it's good to like unpack the problem. And, the problem is really around finding availability. Something that seems so simple, but based upon the problem domain, it can actually get quite complex. For our exercise, I'm actually boiling, as I said, this is based on a system I designed at my previous endeavor. We're going to be building the simplified version of it because in my previous life, it involved event management, and there's all sorts of variables in there. That's not just space booking. There's spaces nested within spaces, and minimum and pricing, and other sorts of rules and exceptions. So we're going to keep it relatively simple. Availability can be thought about in three ways. It could be closed, it could be available, or it could be unavailable. And you're booked. And basically, we can form a calendar tuple. Like, if we're looking at a calendar, it's basically we have a room, the status of it, and a time range in which that status exists. So saying like, hey, the virtual room is booked from 6 p.m. to 7:15 p.m. For this presentation. Okay, fairly, hopefully, fairly digestible nugget of information. Now, Postgres has this wonderful data type that actually makes this problem a lot simpler, and this is the range type. The range types have been around, I think, for close to a decade now, about a decade. And it actually coincided when I joined this, event software management company, and basically, built like effectively an early prototype of an application around it, and like it worked great. Basically, the idea is that you can just store a range of time and perform operations and functions over that range of time. There's some built-in ranges that exist, dates and timestamps, integers, numerics. They're fairly easy to extend that. If you need a range of internet numbers, you can get that right out of the box. And the syntax is like, fairly comfortable. You can do something, it's like select TZ range. And here we go. We can see, the range from 9:30 a.m. to 10:30 a.m. So let me pull up a database real quick so we can look at it. Let's see, here we go. Let's see, and it seems very, it's fairly natural. And if we want to look inside of it, I'll go off script a little bit. What did I do wrong? Okay, I guess I forgot the introspection parameter, but basically I can look inside the range and see, there we go. Yep, so that time is inside the range, which makes sense. And this time is outside the range, so it's going to return false. So like pretty cool, like it simplifies the lookup. Because otherwise you have to do like some complex inequalities and nobody wants to do that. And like that's what ultimately I prefer simple code to complex code because it makes it much easier to digest.
Time ranges is one of the best things which happened with Postgres, honestly. It just solves like so many problems.
Yeah, I learned about that at a Postgres event from the author himself, Jeff Davis. And when he told me about that, I said, I don't need this just yet, but I know I will. So I'm going to buy you beer for the rest of the night.
Would that respect time zones? That operator?
Yes, it respects time zones. Yes.
So if the values are like CST and then it's GMT, it'll know the difference.
Yeah. If it's time with time zone, yeah.
Wow, that's pretty amazing.
Yeah, so I think my clock is in UTC. Let me just double check. Yeah, but if I went to EDT, nope, it's going to fail.
But I mean, it's got to be thinking about the range also on the range you define, right? You created sort of So what range is it? What time zone is it using within the TSTZ range?
So it depends. So this is a timestamp time zone type. So it's whatever time zone is within that timestamp. So by default on my server, it's UTC. Quick diversion to time zone. So again, dates and times. I can actually do a whole talk just on dates and times in Postgres.
Right.
So Postgres supports like the full gamut of time zones. We get it from the TZ data database. Fun fact, like for the first time ever, TZ data, like the TZ database is in the news. Look it up. There's a whole controversy there.
Really? Okay.
Yeah, it's wild. That said, actually internally Postgres maps everything to UTC, but you're able to transfer it between whatever time zone you want. Typically on my local disk, I use Eastern time because that's where I live. On my Kubernetes cluster, I have UTC. Why not?
Sure. Thanks. Yeah.
Cool. All right, so just being cognizant of time, no pun intended. So availability looks something like this. Like you can see the ranges broken up, visually very easily. Like we have a close range from midnight to whatever time this is, available, unavailable, and so on and so forth. And basically, we're always in these contiguous chunks. To efficiently take advantage of availability in our application, we're going to want to be storing like a bunch of these contiguous chunks. I believe in the presence of data here. It makes it much easier to manipulate later on. And essentially like what a day in the life will look like is something like this, where we basically map all those contiguous chunks into ranges and we'll store them in a calendar somewhere. And if I were to copy and paste this into my terminal, we will see that I have a syntax error. Wow, what did I mess up? Oh, okay. Well, this is unimportant. I'll fix it later. So basically, this is what it would look like. So this is relatively easy, I hope. If I explained it well, hopefully it's relatively easy, but it's going to get complicated. For one thing, if we have, if it's a static system, yeah, it's easy, but we have new bookings that come in. We might have new openings. We might have to adjust the time that we're open. And inserting new ranges and dividing them up was challenging. Postgres 14 made this a lot easier, and we're going to talk about that. And like there's an exciting new feature in Postgres 14 that almost mooted having to do this talk. So let's talk about availability. I just showed you the availability for one day. What about days into the future? How far into the future do we build the system? What about days in the past? Do we want to keep that data? Do we need to keep that data? It all adds up, as the system grows and grows. And then, on availability, we need to ensure there are no double bookings. How do we do that? What about overlapping events? How do we account for that, in a real world space? Also handling multiple spaces as well. We just showed one room. Like there's a lot in the real world domain that makes this much more challenging. But as I said, we're going to boil it down, make it a little bit simpler. And through that, we're basically going to build this data model where we're going to have a room. And with our room, we have something called an availability rule. And the availability rule is going to define when I'm going to allow bookings for that room. So basically my available blocks. We can set it by, we basically going to pick the days of the week that were available, like Monday, Tuesday, Wednesday, Thursday, Friday, a start time and end time, and how many weeks into the future we want to generate our rules. From that, we actually generate the actual availability that gets mapped to the calendar. Then we have unavailability, or the booking, and basically we pick the time range in which we're unavailable. So again, October 20th from 6 p.m. to 7:30 p.m. That would be unavailability, and then it goes into the calendar. Then what our system will do is our system will keep that calendar table up to date with the exact state of our room at any given time. And all of our lookups will be against that calendar, because by keeping that calendar in sync, we can very quickly look things up while another part of the system is generating the availability and the unavailability, et cetera. So the idea is that we have half the system is doing the work of being able to generate what the calendar looks like, allowing for us to do the quick calendar lookups. Otherwise, what would happen is that we basically have to calculate the availability on the fly, and that's the costly operation. And you'll see, through the queries to generate the calendar, having to execute those every time, it's not as fast as being able to do a quick lookup. And if you hear a little human in the background, the little human is eating right now. Managing availability. So we know how to store data, but how do we generate initial data in a calendar? How do we generate it against those rules? And how do we ultimately book things? And that's really the job of the application. And that's why we're here today. So to do this, we're going to take advantage of some of the awesome features that Postgres has. There's a few things we're going to explore. One is something called generate series. It's a set returning function that can basically generate a lot of data. And again, we'll talk about this in a few slides. In the previous version of this talk, we spent a bunch of time on recursive queries. And I'm going to cover it just because it's good to know that Postgres can do recursive queries, and they're still useful for things like, in particular, like dealing with graph data or any kind of nested hierarchical structure. But what almost made me like completely throw out this talk was the introduction of multi-ranges. This is a new Postgres 14 feature that both greatly simplified the code and the problem, and actually led to a huge performance boost in it, where I said, oh, maybe we don't need some of these techniques, but like at a certain scale, you will. We'll look at SQL functions, and given Henrietta's talk next month, maybe I'm doing it wrong. We'll find out. Set returning functions are important here. We'll look at PLPG-SQL, the procedure, the built-in Postgres procedural language, as well as triggers. And then we're going to throw a bunch of this stuff out and look at it a completely different way. So let's dive in. So generate series. Often you see in Postgres example posts, people use generate series to create test data. I am certainly guilty of that, but it's more than just for test data. It's actually great at filling in the absence of data. Particularly for reports. Let's say I'm generating a report of how many transactions occurred on a given day. And let's say there's a day where I had 0 transactions. Well, if I just run a query without having that day available, there's going to be a missing day in the report. With generate series, you can basically account and have like every single day in the report, and join it to, and basically, use that as your from table, and then join the rest, do a left outer join on your actual data. It's pretty cool. It's very flexible in that regard. And like one of the best things is that you can run it, against dates and times as well. So, for example, why am I getting syntax? Oh, I know why. It's because PowerPoint inserted.
Yes.
Yeah. Oh man. There we go.
Copy from.
There we go.
From Word or from PowerPoint, from many Microsoft products, they do this like. This is wrong. Yes.
So the syntax is correct in the other one. Okay. So as you can see, we can generate a full year of data. Pretty cool. Recursion. I'm going to touch on this very quickly because it's not as relevant in this example now. But the idea is that basically, if you need to have loops in SQL, you can do it with recursion. It's been around for over a decade. It's pretty cool. One caveat is that you can hit infinite loops if you're not careful. You can also hit cycles as well, which will cause infinite loops. Postgres 14 added some syntactic sugar to help you break out of cycles, which is actually pretty cool. So for instance, doing a factorial, this will hit an infinite loop because it'll just keep going on and on and on. If you don't want an infinite loop, you add a limit. That's also pretty cool because then it's like, oh, okay, only calculate up to 100 factorial. Let's see if I get the syntax error. Yes, I do, because it's inserted all these spaces. Thank you, Microsoft Word. All right. Again, just going at the fact that you can do recursion SQL, we'll see the former method that I built out this application. I'll show briefly, and you'll be so glad that we don't need to deal with this because we have multi-range types. Multi-range types, I was so excited when I saw that these made it in. One of the biggest limitations on dealing with ranges in Postgres was dealing with non-contiguous ranges. So basically, let's say I had something from October 1st to October 3rd, and then October 6th to October 9th. I couldn't really deal with that in a cohesive way. I actually had to build these recursive queries in order to like break ranges apart and then pull them back together. Not in Postgres 14. In Postgres 14, you have the ability to basically deal with these non-contiguous ranges. Essentially, a multi-range is an ordered list of ranges. And this is an important one to look at. So I'm going to try to unmess it up.
This is awesome. Oh, gosh.
Yes.
Oh.
So basically, I have this set of these ranges, and they're discontiguous. So I can do query operations over this entire set. I can even, if need be, I can unnest them so I can get the individual ranges.
So you can do all this like intersect, like include and everything with this like, oh my gosh.
It changes, like this is a game changer, and you're going to see like how much the code from the original talk to this talk is reduced because of this. But yeah, you basically have all the range type operations on it. You can also do range aggregates too, which again, you'll see makes the problem dealing with complex availability much simpler. And it's fast. Like this performs pretty well just based upon some of the testing I did. So yeah, wonderful, wonderful, wonderful new feature. I will take partial credit for the unnest functionality on multi-range types. I've reported it to the hackers list when it was missing in the beta, and I made the argument that the feature was incomplete without it. But definitely major props to Alexander Korotkov, who worked on it and got the multi-range types committed, as well as the unnest function. I'm very proud of the unnest function. I'm biased though, so.
No, wonderful, wonderful. No, that's no, it's just
game changer. Like this is a total game changer for dealing with range types. Like man, like I could go on all day.
Yeah, no, I hear you. Yeah, I'm dealing with range types a lot. I just hear you. Like 200%. Yeah.
Functions. Functions are pretty cool. And again, I came from an application developer background. Now I do much more on the operations side. And as app devs, you kind of get like this like funny feeling about doing functions in the database. Like there's certainly things like I do like 100% agree should be functions in the database, and you'll certainly see some of those tonight. So what's great about functions in Postgres is that they're actually very robust. In part because you can write them in procedural languages, and not just PL PGSQL, but out of the box you get PL Python, PL Perl, and PL Tickle. Lots of other languages available as well. I think I cover it in another slide. Functions have all sorts of different properties in which you can apply to them. For instance, immutable functions you can actually use as part of expression indexes in Postgres. So you can actually have some pretty complex, fast indexing lookups based upon those functions. Stable functions are great for select queries. If you know that basically the data is not going to change outside of the transaction. By labeling a function as stable, the Postgres optimizer or the plan in the optimizer can do some work against it to speed things up. And the other thing I'll mention is that Postgres 11 introduced stored procedures, where basically you can apply transaction control within a function. So if you need to do like multiple commits or something within the stored procedure, you can do it. Those coming from Oracle or other proprietary databases are familiar with those. Postgres 14 adds the ability to actually get output data from the stored procedures as well, which is, again, huge, particularly for the people coming from the proprietary database world. So yay, Postgres.
Yeah.
I'm gonna touch on functions real quick because we're gonna look at a ton of them. I took the factorial function that we had and turned it into a immutable parallel safe function, and basically said like, hey, if you can parallelize this somehow and turn it into an index, you can do that. One thing I will pause on though is the set returning function. So in addition to being able for Postgres functions to return single values, you can return sets of values. So basically, similar to like what we find in like returning from a table. So in this function, I basically say, hey, return an ordered list of all the factorials up to n. So if this were 100 factorial, it would return in an ordered list of all of the 1, 2, 6, 10, and so on and so forth. So as another example of a built-in set returning function is the unnest function, because the unnest function basically unwraps the multi-range type and then allows you to be able to interface with every single record. Setup is very useful, but you can actually get a little bit better in Postgres with something called a table returning function, where you basically can define the structure of the set of data that's coming out. And there's actually performance benefits to this I found in my previous life, where I was basically building this availability application. We were returning sets of data. Originally I was using setup. I then gave a specific data definition to it using table, and actually my query sped up because Postgres is smart, is able to be smarter. And I was like, oh, I know it's this type, I know it's this structure, I can do additional planning against it. Pretty cool. I forget like if I read that in the documentation or I stumbled across that or where it is, but I do want to mention that because this is we're essentially going to be returning tables, essentially these structures, when we see the availability application. Procedural languages. I actually touched on this before, so I'm just going to gloss over it. Basically, you can write your favorite programming language as a stored function, a stored procedure in Postgres. Yay! So we're going to be using PL PGSQL, and here's the factorial function written in an iterative way. Okay. Triggers. So triggers, I'm going to call, in terms of like building out this application, triggers are sort of, I don't want to say they're the legacy way of doing it because triggers have their uses, but for the problem domain we're looking at today, this was the initial way that I'd implemented it, and we'll see that we hit some challenges with it. What's nice about triggers is that they allow you to take actions based upon events that happen. It could be a data change. It could be something changes in your schema, your access controls, etc. And what's nice about triggers too is that they're atomic. Basically, it's all or nothing. If within a transaction, it's all or nothing. If it's something the trigger fails or you cancel something in the trigger, then the transaction rolls back. When you define a trigger function, it needs to return a trigger or an event trigger. If you return null, basically you cancel what's going on. And this is why you gotta be careful when you're writing triggers, because there are these keywords old and new that represent the state of your data in the trigger, and that's ultimately what you're returning in them. But if you return old on an insert trigger or new on a delete trigger, you're actually returning null because there is no old data when you're inserting, you only have new data. And there's no new data when you're deleting because you deleted it. You only have old data. Little gotcha. I've burned myself in production on that before. And there's some other notes here on triggers. What's nice is that we're going to spend some time building up our application in, let's call it the traditional way of trying to keep everything synchronized. And then we're going to throw that all out and do it in a different way. So let's build the system. And as I said, we're going to scan the code. It'll be available for download probably tomorrow. I've gone on a whole binge cleaning up the code. I'm going to put it in a GitHub repo to make it much more easily accessible rather than sending Henrietta a random tar file. And you have to trust me that I didn't put anything nasty in the tar file. So here's the code. Is this legible? I can make it a little bit bigger if need be.
Yeah.
I'm good.
Yeah. It's all good.
Okay. Awesome. All right, so here's our schema. Again, it looks exactly like we did before. Note the use, I don't use serial types. I use generated by default as identity. This is a nice feature added in Postgres 10. It's basically an alias for serial. But this is in the SQL standard, so you should be using it. All right, so everything here is fairly, you'll be able to look at this in your own time, but basically we set everything up. So first, some helper functions. So when we insert a room, we basically need to pre-populate our calendar. Because remember, our calendar is effectively like the cache layer of all the actual availability for the quick lookups. And we insert a room, basically, we just know we're closed. Here's our generate series function. We basically say like, hey, when you insert a room, insert just a year's worth of closed data. And that's pretty cool. Because essentially we just with like effectively one line of SQL, we can insert all of that data. We add a trigger, so basically when we insert a room, run this function. Next, availability rule bulk insert. This is a helper function that I wrote to bulk insert availability once we add an availability rule. So recall that an availability rule in the case of our application is a generic rule that says, plan my availability around these parameters. So like Monday through Friday, 9 to 5, I'm available. Based upon that template, insert the actual availability into the calendar. This is the function that handles it. There's some logic in it to check for am I going into the next day or not based upon how the rule was set up. Beyond that, it basically obeys whatever you put in the rule. There's a trigger basically when you insert an availability rule or update an availability rule, or if you insert an update availability rule, it basically decides how to run that function or perform any updates on the availability. The actual availability then gets synchronized to the calendar, which we'll see in a second, so that you can ultimately look that up. Why is there no delete? There's no delete because we are practicing good relational integrity. So as you see on our availability rule ID, we are putting a foreign key, or basically references back to availability rules such that If the availability rule is deleted, we delete ourselves. And that cascades all the way down. Pretty handy, in my humble opinion. There's overhead to that, though, just beware. Essentially, it's creating a trigger internally in Postgres to be able to do that work. So now we are going to pause a second. We're now at the point where we can start futzing with the actual availability, or basically, creating the calendar. Before I show this function, I'm going to go back to the old application to show you what we had to do. And again, I know I'm zooming through this a little bit. All will be revealed in the fullness of time. So when generating the calendar, I had broken it up into 2 steps. First, generating the availability, so basically merging the closed data with the availability, and then merging the unavailability with the availability in the closed data. Why did I break it out into 2 separate functions? Well, here's the function to just generate the availability. And I'm scanning through it quickly. Notice it's like about 100 lines just to do that. And then it's another 100 lines to be able to do the unavailability. Why is that? We had to use this messy recursive, actually, no, sorry, I take that back. It's like 150 lines. We had this messy recursive function to be able to basically split apart the ranges, bring them back together, because remember, Postgres range types, you weren't able to break them up. You could not have non-contiguous ranges. So we had, basically had to find a way to be able to deal with that and pull it all together. This is, I might just put this function back up in the example code so you can see the level of pain it is. But as you can imagine, that we have this one recursive function just to generate the calendar availability. And then we have this other recursive function to, tie it all together with the booked offerings. That's going to take some time. Like, this is not free. This is a lot of work going on. I will give another fun fact. In the real world application, actually, I might need to fix it here. So in the real world application, I add a union all here. And a union all in a recursive function basically includes everything. Whereas if you just do a union in a recursive function, it will remove duplicates and smush it down. In the real world, I had a union all initially. And at one point, things were getting really, really slow and bogged down. And it made no sense based upon the amount of data that we have. I did some analysis and I realized, like there were some of our venues had just the way their spaces were structured. It was basically blowing the availability tree out of proportion and ultimately actually causing crashes at a certain point. I switched it to union, problem went away, and system sped up. I think it was 100 times I measured it. So of course I got to brag hey, I sped up the system 100 times. Oh, but by the way, I was the person who caused that 100x slowdown. So that's the trade-off there. So why did I take this long detour to explain the level of pain of that was? So let's look at the new functions, and I split them up. So first, here's the generate available function, and this is it. It fits completely on my screen. Look how much nicer it is. It's basically all I have to do is, I do a little bit of SQL trickery here. This has to deal with being able to get a space that just has some closed or the lack of close time in it. But essentially, all I have to do is turn my, the range I'm trying to create the availability, this range is probably a given day. So let's say October 20th. October 20th from, midnight to midnight. Then grab all the available data, all the data we have on availability that day, aggregate it together, do a multi-range difference. So basically, I get to see my data split up. And then that's it. I'm basically done. I now know all my closed blocks, because basically I take all my available blocks, subtract them out from my closed blocks. I have my closed blocks. And then I just grab my available blocks and I smush them all together. And there we go. I know when I'm closed and when I'm available. And because of the multi-ranges, I don't need to think about it. I don't need to write a 150-line recursive function that took about 2 weeks to perfect, and then another 2 weeks to debug why production was so slow. This, this simplifies the problem. I probably should retitle the talk to upgrade to Postgres 14. Here's why. And then finally, we generate the calendar. And from generating the calendar, it's as simple as I'm grabbing, all, that close in the availability blocks, and then subtracting out the unavailability blocks. So I know, I know what those new ranges are at. And then I combine that with the unavailability blocks, smush them together. I have my calendar. I understand like this might feel a little bit abstract. We're just looking at the code. I'm rushing through it a bit. We'll see it in action. And again, I will make all the code available. But this is the heart of the presentation, and at least the heart of the functionality of the application. Beyond that, there's some trigger functions that wrap everything together, and so on and so forth. So let's install this. Enough chit chat. Let's build our application. All right, everything's installed. So let's demo it. I might have some slides that say like, let's demo. Okay, let's demo, yay. All right, so I'm gonna turn on the timing so we can see how long it takes. Now let's keep everything directional here. I'm running this on a Kubernetes instance. So I'm running this in a container on a virtual machine on a laptop. All timing here is directional. I did not tune anything. So let's create a room. And I call this Chicago Pug virtual room. Cool, all right, it's fairly quick. Let's look at the calendar. So I chose October 28th as the day to look at things. So as I described, we basically created all the availability in the calendar. And because we haven't set any availability rules, all we know is that we're closed basically all day. If we look into the calendar, we'll see that we have about a year worth of this data. So this is pretty boring so far, but the exciting thing is that we basically inserted data into our room and we generated a calendar. That's pretty cool. All right, so let's insert some actual availability rules. So basically we're going to say we can book, in general, we're allowing people to book virtual Chicago Pug events from 8 a.m. to 1 p.m. and then 4 p.m. to 10 p.m. Okay, so it took about half a second to insert all that data. But let's see what a day in the life looks like. What does our calendar look like on October 28th? Okay, well, it's exactly what we want it to be. It's that we're closed from midnight to 8 a.m. Then from 8 a.m. to 1 p.m. we're open. Then we're closed again from 1 p.m. to 4 p.m. And so on and so forth. And that's pretty cool. We basically kept everything in sync. And while we paid some upfront pain to insert that data, again, notice the lookup is nothing. It's 7 milliseconds. That's perfect for a web transaction. So let's say what happens if we update the rule. Let's say like, all right, I want to update the rule. I want to stay open till 11 p.m. Okay, so again, 200 milliseconds. That's okay performance-wise. You could probably do in a web transaction, but think about scaling. If we have a lot of these things, that's going to really slow down. But we see that the update applied. We now stay open until 11 p.m. So what happens if we delete our availability rule? All right, so we delete it. So again, recall that we're taking advantage of Postgres's referential integrity to handle the delete. But it works, right? We basically deleted all of our openings, and now we're always closed. Back to square one. But being always closed is boring. So actually, I deleted the room as well. So if we delete the room, we can see that then there's nothing in the calendar. All right, let's go back and actually insert some real data. Okay, so let's insert a booking. So recall that unavailability is the booking. So let's say we're booking our virtual event from 9 a.m. to noon. Cool, we have now done that. And we can see that, hey, the booking is there from 9 a.m. to noon. Cool, it works. Everything's in sync. The lookup is still quick. Even inserting the booking, was pretty quick as well. So that's good. Again, we might need to be a little, we might need to think about scale a little bit, but it's fairly, it's fairly straightforward. And look, let's insert another booking. You're at your typical meetup time. 6 p.m. to 8 p.m. And again, our data is there. We have a full calendar. That's pretty cool. I think so. Okay, and so on and so forth. We could see the event updating. And let me delete. Let me delete a booking. Prove that everything still works. Yeah, everything still works. Okay, so that's pretty cool. We kept everything in sync. And if we have any takeaways from this, First, it's always test your live demos before running them, and you'll have much success. Though I will say, is as soon as you move things into the cloud, like all bets are off. Like this is where I miss the application developer work. When I do operational demos, it's like, all right, well, let's see. I'll note that the availability rule inserts took some time. This was at least greater than 350 milliseconds. The old slide read that it was far more painful. So this is actually kind of cool that the pain is a lot less thanks to the multi-ranges. We don't have to do this crazy recursive query. But inserting, updating, not too painful, and the lookups are very fast. So what about if we do it at web scale? I believe, just for the sake of time, I basically stored all the times here. Essentially, we generate a bunch of rooms. Doesn't take too long, less than half a second. Insert availability rules, took about 20 seconds. In the old system, with the recursive query, it would take well over a minute. Same thing with inserting bookings, it would take well over a minute as well. A minute and a half. So we can see that the advertisement is multi-ranges make things a lot better. The other advertisements, some of the techniques we'll look at, you might need to get to a larger scale before you need to implement them, but that's okay. We're going to look at the techniques anyway. Lookups are still very fast, in this system, and then that's part of the point is that we're solving two problems: being able to insert and manage the data, and being able to do the lookups. And at scale, because we have that cache table, we have the range types, we have the indexes on the range types. Lookups are still fast. What was interesting though with the recursive CTE is that the generation time increased far more significantly than the multi-range types. Like recursive CTE is like beyond linear in terms of the time scaling. Multi-range types, it actually was still pretty fast. Like I think it was sublinear in terms of the speed up, which seems a little weird. Lookups are still fast. But we're going to hit a certain scale. And we can now take advantage of yet another Postgres feature, once we get to that scale, called logical decoding. Logical decoding is added in Postgres 9.4, and essentially it allows you to replay all logical changes made to the database. Essentially, it's your transaction stream. So the ordered list of all the transactions that occur in the database, come out of the stream. You create a logical replication slot on your database. And from there, you basically you attach a receiver to it, and it can consume all the changes coming in. The slot keeps track of the last change that was read by the receiver. So basically, the receiver has to acknowledge each change. Like a receiver could read the change, but if it doesn't acknowledge that it got it, Postgres will hold on to that transaction until it gets replayed. If the receiver disconnects, the slot will, as I said, the slot ensures it holds that change forever. Caveat: if you don't ever acknowledge that slot, Postgres will keep retaining your write-ahead logs forever and ever and ever until you run out of disk. Postgres 13 added a feature to basically break the slot in that case. That way you don't run out of disk, if you so choose. This is also the advertisement for having monitoring. This is actually wrong. I say only changes from tables to primary keys are relayed. Actually, if you set a replica identity, that will allow you to relay effectively, all the changes from that. This is the basis for logical replication. And logical replication, also introduced in Postgres 10, provides another way of being able to get this data out of it. We're going to look at logical decoding, though. Just because the example was originally built off of this, it's still, very useful for it. Logical replication, and actually, let me get to the next slide. I'll talk a little bit about that. So you get logical decoding out of the box from Postgres with this thing it has called a test decoder, which is some custom format that shows you what your changes look like. You'd have to write a custom parser to read those changes. You don't want to do that. There's several output plugins and libraries available for being able to read changes from the logical decoding stream. The most popular is Vault to JSON. It's written by Euler Tavera, a longtime Postgres contributor. It's what we're going to use in this example today. There's a few others as well. The other one that's really popular is Debezium. Debezium basically It actually works with multiple databases. I believe Postgres, MySQL, Mongo, some others. And it both works with logical decoding and logical replication. What's nice about logical replication is that you can actually target exactly what you want to read out of a Postgres database, whereas logical decoding, you're reading the entire logical stream in. So basically buyer beware which one you want to use. I ultimately want to update this talk to use Debezium, but I actually thought it's still worth it to see how to work with the entire logical decoding stream. I have a separate talk out there. It's called like Postgres on the Edge that uses Debezium. If you're curious about that, check it out. It's edge computing stuff. So yeah, it's pretty cool because basically you as I said, you're able to get all the transactions out of the database, and that's an important part in terms of keeping things synchronized. A bunch of Postgres drivers already support logical decoding. Here they are. Today we're going to use psychopg2 because I wrote these examples in Python. Figure out which one works best for you in your native programming language. A lot of basically any of the libpq drivers should support it, but they need to be able to provide the interface for you to do it, such as what psychopg2 does. You need to set a few things in Postgres. You need to make sure your wall level is logical. I believe Postgres defaults to it today. You need to at least have a couple wall senders and replication slots available. You need to make sure you have the replication privilege in the pghba.conf. Never use trust outside of development. Actually, in the case of what we're going to use, I'm using the Crunchy Postgres operator for this. I'm using the super user account. The operator container does come with wall to JSON, so it just made it easier to set up the example. And we're going to set up a logical replication slot in order to get this to work. So basically, the idea is that we know it takes time to regenerate the calendar whenever we change, availability, unavailability, a rule. But we also want to make sure that when these rules changes, we need to ensure that one, the change, we can basically emulate the behavior of a trigger. That essentially we can atomically change it even if we're doing it out of band. And we also want to make sure the changes, when we do changes, like all users have a good experience. So the person managing the calendar has as good of an experience as the person who is consuming the calendar. This was a very big deal in my previous life because we essentially had two sets of users, the people who were operating the venues, and then the people who were going to the venues, with the events, looking up availability. So how can we do this? We can replace triggers. We can use the same data model as before, but without the triggers. We're going to eliminate all the triggers, but we're still going to be able to replay all of the changes no matter what happens. We're going to use Python. We have some separate Python scripts to do this. Similar to what we did with triggers, we are moving the work outside the transaction. So the work won't be atomic in the transaction itself, but we've essentially designed our system to guarantee that, by using logical decoding and properly acknowledging the transactions, we're designing the system to properly replay all the changes that occur in the database. So, let's review a little bit of how this would work. So I'm actually not going to run this example for the sake of time, but the idea is that I would connect to the database, with this special replication connection. Essentially saying, please replay all the changes to me. Excuse me, after I create my logical decoding slot. And we can basically stream in all the changes. And basically, when we see a change, we can choose the change that we want and take an action upon it. If I were to run this example, we would see every single change to our data that goes through the database. And well, I'll show this example later. When we set up the more complex system. Now, there is a problem here, and I'm going to jump right into the problem, which is first I need to delete our schema to set it up for the next example. I just want to clear out any of the leftover functions. I realized I forgot to add these to the script. So the first problem is I didn't script everything. Oh no. Shoot. names from insert and web. Insert. Okay, that should be it. Yeah, cool. Okay. All right. So there's a few problems with the design that I'm presenting here. Basically, I created a Python program that reads in the logical stream and then takes actions on it. But if processing a change takes a lot of time, it'll create a backlog of changes. And then a backlog means that the Postgres server needs to retain more wall logs. And retaining too many wall logs can lead to running out of disk space. And running out of disk space leads to a very bad time. I did run into this in production in the sense of, we ended up getting a little bit too bottlenecked. And I think we had to replay about 35 gigabytes of write-ahead logs. The thing was that, it doesn't sound too terrible. I mean, 35 gigabytes, what is it? That's basically every single change that occurred. But then we had changes begetting more changes, begetting more changes. So they kind of like requeued, and like it took a while to get through everything. So there is a little bit of a better way. And that's basically eliminating the bottleneck by distributing the workload. What do I mean by that? As long as we have a durable message queuing system that can store the write-ahead log changes, we can queue those up there and then distribute the workload to have individual workers acting upon it. We can still ensure the changes are worked on in order. We can still ensure that all the write-ahead logs get acknowledged and all the changes get acknowledged. So we can remove the write-ahead bloat and still make sure that we are synchronize everything in order. And we can divide and conquer the workload. So for instance, I can set up a worker for each, for each particular queue. Let's say a queue of room changes, a queue of availability rule changes, a queue of booking changes, etc. I have multiple workers acting upon different topics. So distribute the workload, have everything, be able to parallelize the process a little bit more, ensure that we don't get a bottleneck. How do we do that? In this example, we're going to use Kafka. Kafka is a durable messaging processing system. It's a distributed system. It acts upon these things called streams, which is essentially what the write-ahead log is. It's your stream of all your Postgres changes. It has high availability. It can be parallelized. It's very advanced software. We probably just do a talk entirely on Kafka. So this could be a homegrown system for interfacing with Kafka. You can actually also accomplish this with Debezium, which in some ways like standardizes, the interface for working with Kafka and Postgres in a way. I definitely recommend doing that, and maybe that's my next talk at Chicago Pug, which is how to use Debezium to do change data capture, or I guess I do that in the context of edge computing. We could sneak that in as well. But effectively, the architecture looks like this. We have a Postgres database. We have a Python program, which I call the wall consumer, which basically will get the entire write-ahead log stream. Based upon the changes in that stream, it'll push them into particular Kafka topics. That's what they call the messaging queues. And then on the other end, we have consumers reading things off those queues, taking actions upon them, and effectively putting changes back in the Postgres database. So I do need an arrow that goes back to Postgres from there. Again, my plug for Debezium is that with Debezium, you can interface directly with Postgres logical replication, so you don't have to read in every single change of the database. You only have to read in the changes that you want. Cool. So let me actually, I'm going to go back to the code. Here's what a wall consumer looks like. What does a wall consumer look like? Looks like this. So effectively, I call it the stream consumer, but no, sorry, I take that back. This is not it. There we go. This is it. So wall consumer, like literally all it does is that it connects to the Postgres database. It grabs the change. It grabs all the changes that come in. It determines like, is this an applicable table that we're watching? I know I keep a list of tables over here. If it is, we push the change into the Kafka queue. We acknowledge the change in Postgres. Otherwise, we just throw the change out and acknowledge the change in Postgres. That way, we keep the wall stream clear. Once it's in Kafka, you basically fire up what I call a worker. And the worker, the base of the worker is that it pulls off the change, it puts it into a format that's easy to digest for the individual consumers that we have. And then when we know that the transaction's been committed, whatever changes we make have been committed, we then acknowledge it in Kafka. So that way we're guaranteed that the change occurs and gets replayed. So for example, with our rooms, we know that on insert, we want to insert when we insert a new room, we want to put into our calendar that, hey, there's a new room, everything, make sure everything is closed. That will happen. We get a new availability rule. It's like, oh, hey, we get a new availability rule. Insert availability based upon the rule that comes in. And then when there's an availability entry inserted, we say like, okay, great. Run that magical multi-range calendar function and update the calendar with the new availability rules. So effectively, what we did is that we took the triggers from the previous implementation of the application and moved them into this producer-consumer system, still following the same rules. Everything is atomic. It's just occurring at different parts of the process because we're respecting transactions and we're using transactional systems to do that. And that, in my mind, is really, really cool. So let's see, where are we at now? We're at demoing the application. Cool. As my little human did not sleep as well as I wanted her to last night, let me make sure I'm able to do this correctly. So as I mentioned, I'm going to need to reset up our application. And the only thing I want you to notice on this is that our schema looks the same as before. And we have some helper functions, just as we did before, but there's no triggers. That's pretty cool. All right, so we've recreated the schema. We need to recreate the replication, or we need to create a replication slot. Fortunately, it's fairly easy to do. I created a replication slot. I called it schedule. I'm using the wall to JSON logical decoder. As I mentioned, it's available in the containers that come with the open source Postgres operator, and that's created. Cool. Now we're gonna load that application. So I apologize. That's probably illegible. No, I can't control my screen. Okay. So as I mentioned, I put everything up on Kubernetes because why not? How many people have said that? So I want to show that I have Kafka already running. I have my database already running. Here's our Kafka broker. And I created a bunch of manifests that will make it easy to get that wall consumer as well as all those, the wall consumer and the other consumers all up and running. Because why not? Kubernetes, it's fun. Said. All right, so this is bringing our system, up and running. Cool. All of our applications are running. I'm going to tail the wall consumer since we haven't seen what it looks like to see all the Postgres changes going through a database. Sorry, all the Postgres changes going through the wall consumer. Please forgive me. My, as mentioned, my brain's getting a little loopy now. Okay, so let's run through the demo. And there's a few things we want to track in the demo this time around. We want to track how long it takes for things to insert, and we want to track how quick the lookups are, and as well as when the data gets into the lookup. So first things first, let's insert the room data. And if we go to here, we can see, okay, we have this room insert change come through. And let's see what happens with our calendar. All right, exactly what we thought, that we basically insert that in our calendar, the data is closed. Cool, so the room insert was pretty quick. I believe it was probably quicker than the original query, but I did not load that. But we remember the inserting into availability rule, this was about half a second to run this query. Well, this is way faster than half a second. It only took about 10 milliseconds. We can see all these changes got into our wall consumer. It got pushed into Kafka. And now if we look at our, oh no. that didn't work. And so when I now look at our calendar, we can see like, hey, this is exactly like the first example. All the data is there. Cool. All right. What happens if I delete the availability rule? Now remember, like this took this wasn't too slow, but like it wasn't 5 milliseconds slow. And we look back up at our calendar. All right, we're back to square one. If we delete our room, now we're truly back to square one. But okay, everything is still synchronized. So let's build up a more complex example. So let's set up all of our availability rules. All right, pretty fast to do. Everything, all the changes are getting replayed. We're synchronizing the data. Oh, my keyboard is acting up. I don't know why. All right, okay, we're gonna stick to copy and paste since the read line's not working. Cool. All right, so we're back to where we were before. So let's insert a booking. Again, pretty fast. And let's do a lookup. Lookups is still fast. Our booking is there. Let's insert another booking. Cool. Still, there we go. It's still, the system's keeping everything synced. So what's cool from the user experience is that for the people who are managing the space, if I'm doing this through a website, all these transactions are fast. And if I'm the person who's looking it up, I'm still getting the data pretty much updated, in real time or close to real time. Basically it's down to how much processing power you have on the Kafka queues. But what happens if I do an update? Let's say I update the booking, I move it back an hour earlier. There you go. That's almost instantaneous. There it is. Move back an hour. And if I delete the booking, the first event cancels. Boom, off. So that's pretty cool. We've now basically made the equivalent user experience for both the people managing the space as well as the people who are accessing the calendar. That's really cool. And this is what I love about Postgres is that it gives you all the solutions to solve even let's call this like real-time complex scheduling applications. And again, like we have to extrapolate it a little bit too, because like one, as I said, with the multi-range support, you might be able to kick the can a little bit on having to implement the solution, a solution like this. But even still, if you do implement a solution like this, like you're getting even more bang for your buck because like the cost of computation of doing something around availability is so much cheaper with a multi-range type. And then you can distribute the transactional load as well. If you do have CPU and if you're using something like Kubernetes where it's very easy to spin up more resources, debatable, you have to also spend a lot of resources to do that. Yeah, it makes it much easier to scale out, fan out and scale out this problem. And ultimately perform better. Alrighty. So what did we learn? Logical decoding, and actually I'd like to extend this to logical replication, allows the bulk, it allowed the bulk inserts to occur significantly faster from a transactional view. This lesson is not true anymore. In the previous example, I still had delete triggers, but I was actually able to remove the delete triggers thanks to the replica identities. There's still a potential bottleneck for a long-running execution. If a particular query takes a long time in one of those queues or consumers, that could end up being the bottleneck. But instead of bottlenecking like the entire system, like let's say you only had a single consumer reading all the changes and taking action, you can basically isolate that bottleneck to that specific consumer. Isolate the problem there, give that consumer more resources, whatever you need to do. Also, newer versions of Postgres just keep making it easier to build applications and scale out. One of the things I get to work on every year for the Postgres community is the major, the press release for the major version. And when I was looking at all the features added to Postgres 14, what really struck me was the emphasis on distributed workloads. There are a lot of new things brought to the logical replication system that make it easier to deal with, in particular, actually larger transactions, long-running transactions. And then the ability to do parallel query across Postgres databases using the foreign data wrapper system. Those are two ones that come to the top of mind. But it's just this continued work on not only make it easy for application developers to write code like with multi-range types, but make it easier to operate it at a larger scale. So in conclusion, Postgres is robust. I've been saying this for years. This is why like I love it so much. This is why I would design my applications around Postgres. And coming again from more of an application developer background as an operations background, why I just love Postgres and just like touting like here's some crazy thing you can do with it. Oh, by the way, this is actually from a real world problem. Triggers do keep your data in sync, by the way, and this is not to knock triggers. Like the triggers have a time and place, and for a lot of systems, like they're totally fine. But there's overhead. There's performance overhead, and particularly because they are transactional, and that's great. They should be transactional, but if you're able to push out your transactional workload into a distributed transactional system, and it makes sense for what you're working on, you can transfer that computational load elsewhere and speed up other parts of your system, particularly like your web applications that are accessing their database. It's not a panacea. Like I'm not peddling snake oil. I'm offering an example architecture for how you can do something. It may work for your setup, particularly if you're dealing with availability. This might help that problem domain. It may not. Like I said at the beginning of the talk, like the idea is to inspire that hopefully you learned something new from this. You saw some feature you never heard of before, or you saw a new way to like put together a bunch of different features and explore some new technologies out there that work with Postgres. So I believe this was a little bit over an hour. Normally I have to do this in about 45 to 50 minutes, but what I like about user groups is that we can go a little bit longer and have a little bit more fun with it. So I will conclude. I haven't talked this long consecutively in a while. My voice is getting a little bit parched, but I am, of course, happy to answer any questions.
Wow. Jonathan, thank you. That is awesome. I don't know how about the rest. I learned actually a lot. And this like ranges thing, it's a revolution, to what I'm doing. I just cannot say enough about how it makes life easier. And I never knew about logical decoding, believe it or not. It had been for a while and I never used it. I even did not know what to look for. So this also opens for me like the whole world of new possibilities of problems I was trying to solve. So for me, there are like lots of takeaways. Just wow. All right. Well, so thank you. So questions. Well, yes. If nobody stops me, I'll keep talking.
Yeah, hi. I'm Siva. I do have a question. So what's really interesting about this is that, when you do have that wall, you kind of lose that like FIFO ordering of the wall if you have more than one partition on a Kafka topic, right? So it's so is it usually is one partition is enough to keep up with pushing the wall into Kafka?
Yeah, so again, it depends on what scale you're at. In the case, in my previous life, one partition was enough for what we were dealing with. If you're getting beyond, if you have to get to the point where you're beyond one partition, then you need to make sure you store some additional data in your tuple so you're able to like make sense of everything. So effectively, you need to version your rows, and each time you make a change, you would increment the version count. So that way, you know what order you're in. But again, this is this gets into essentially an even more like advanced locking type system there. I guess I was fortunate I didn't have to deal with it at that scale. Though that said, I'm taking a note of looking into this because now you've piqued my interest and I would like to know how I would design it.
Yeah, if you could do it once you figure that out, if you can do the meetup, another meetup of whatever you figured out, that would be great. Because we're definitely.
I feel like it's consulting work. no, but yeah, if I would certainly I could certainly add a slide on it once I figure it out.
Okay, so there are actually questions in the chat, Jonathan.
I have a question too.
Yeah, okay, go ahead.
So, Jonathan, it's impressive what you presented. It's like a company in an hour or something like this. I work with Debezium too. One issue we have is when a large object is built, like an index or a materialized view, Debezium starts not to, it's stuck, for a period of time. I think that's the issue with Debezium, I'm not sure. Another thing, logical replication, it's possible in Postgres 11 to filter the tables you want to replicate. Yes. So that makes it much easier to focus only what's interesting for you or build multiple replications.
Correct.
The only question is if you saw the issue with large objects created that block the replication or Debezium.
Yeah, when I originally built the system, Debezium did not exist. So I've not seen that personally. I am actually going to try, again, taking notes. I do want to stress test that with Debezium to see if I can reproduce that. I'm also curious if that occurs with Postgres 14. In part because Postgres 14 added the ability to stream in-progress transactions. Now, I don't know what that means for indexing. I mean, the only thing I can think of with indexing is, some sort of lock being put on the table. But if you're creating the index concurrently, that should not be an issue. I'd have to look into that.
We had mostly the issue with materialized view. Because that's a replication, logical replication cannot, at least 11 cannot replicate it, but it's accumulating in the logs. And we work on Aurora, so we have not the option for 14. It's only 13 now in AWS Aurora. So I don't know 14 yet. But I'm very interested in what you presented to test Aurora for Postgres 14.
Well, effectively, what this solution is, it's effectively an incrementally updatable materialized view. That's what that calendar table is. It's a materialized view, what's called a table, and it's incrementally updated. And we actually, in my previous life, I initially had implemented our calendar system using a materialized view. But I was hitting performance issues with it, and some of it could have been, some of it could be my code, some of it was pre-parallel query, and refreshing materialized view supporting parallel query. I think that was actually a Postgres 14 feature as well. It was 13 or 14, and maybe some of that would have helped doing it. But really, the solution is incrementally updated materialized views. I know there's been a patch in progress for that for a couple of years. And actually, that would be a huge feature. Again, that might be a feature that totally, makes this talk, thrown out, because that's ultimately what the solution is, to be determined. And we have to see what happens when it's finally committed.
It would be interesting. I kind of gave up on waiting for the incremental update of materialized view since Oracle had it for 20 years or so. I think in my practical work, I just switched to tables with incremental updates instead of materialized view. So, if it will be actually implemented, then wow, we need to get back to using materialized views.
Yeah. So there's a question in the chat. Multi-JSON decoding question. How does that handle DDL changes? Logical replication is bittermeat when type changes occur. Yep. So the logical decoding stream does not have DDL. If you want to be able to process DDL changes, you would need to use an event trigger. Basically, you'd have to keep a table that you log so you could send an event trigger on DDL changes, log that to a table, and then have said change, replicate over the logical decoding stream, take that change, accept it, make the update, etc. That sounds like a lot of extra work, but that's the closest way you can do that. I was actually at one point I was trying to write something to like parse like the physical write-ahead log stream to be able to get the DDL changes. I did not get very far though, as I'm not. I would about to say I'm not a protocol person. I know enough about the authentication protocols, but beyond that, it's a lot. parsing the wall stream is a lot. Like it's amazing what goes on in there.
Yeah, thank you.
Yep, you're welcome.
We tested a bit Debezium and logical replication with changing primary keys also. And somehow Debezium can sync through a restart, to a change of primary keys or so, but clearly crashes after you change a table that's under replication, you change the primary key or so. Other columns are not so difficult, but primary keys, of course, generate major issues.
Yeah, well, in some ways, solving this problem gets Postgres closer for a true like active multi-master, whatever you call it, support. I will plug a blog I have on the Crunchy Data blog that shows one way to get to that, actually using lateral replication, but you're responsible for your own DDL. That's the trade-off. But it works, and you can avoid conflicts.
So John, I guess I'm curious about any thoughts on like the notify function feature of Postgres as a way to sort of offline the transaction or make it out of band, as you were saying.
Yeah, it is and it isn't. I haven't played with it too much. I've only played with it from the PSQL terminal. I haven't really played with it too much from a programming language. That's one way to do it. As far as I know, like it's like I think listen notify still is like within a transaction in a way. I think I have to look this up. I remember looking at this like a long time ago. And I don't want to give the wrong answer to this. But I think the reason why you see things like Debezium change data capture solutions like that is that you're able to pull those changes directly from the write-ahead log stream. I think I want to say like it's a little less. You're guaranteed that atomicity. You're guaranteed that you have the transactions in there. Listen notify could be a little bit brittle in that regard.
Yeah, you're definitely not guaranteed 100% reliability with listen notify versus with Kafka where you have a persistent stream. So we've run into a lot of trouble trying to do listen notify for this kind of system.
So I guess, Lucas, because I guess I was thinking you could listen notify to yourself, right? Like to your own PG instance, and then you don't need the extra infrastructure and all that stuff. Is that? I mean, I'm curious what problems you guys encountered, or what made it not reliable, I guess.
It's all your sort of edge cases, but a database crash and restart gets to be troublesome. Okay. Anything where you're basically needing to replay something is a real problem. There were a few other cases where we saw trouble, but that's really the biggest one.
Okay. So it's just putting it into the wall basically avoids that problem, right?
Right.
Okay, cool. Got it. Thanks. Good.
Okay. Any more questions? I'm just conscious of Jonathan is like 1 hour ahead, and having little human also does not help plus extra hour.
So it's a one more nap time for little human before we start the bedtime routine.
All right. Okay.
Little human also got her 4-month shots yesterday, so she's been very sleepy and a little fussy.
Mm-hmm.
Yeah, thanks. This is great. I mean, it's
thank you. Yeah, thank you for having me.
Like full breath, like start from the problem, how I solve. Excellent. Yeah. Thanks.
No, thank you so much. That was just extraordinary presentation. Getting knowledge in, and so if you will be able to give us the code and everything, I think it is great learning experience. Thank you.
Yeah. So I'm working to clean up the code and make it more general, I had things embedded in it, like, I started my registry.cats container registry, which I don't think, most people have. So I'm just working on cleaning up the examples a bit, and I'll have it on a GitHub repo soon. When I share the slides, I'll also include the link to it in the talk, but I'll make sure I'll put it in the Chicago Pug meetup. But I'm hoping to come out there again next year. I've actually not been to Chicago, I think, since the last time I came to the user group. So I know this might end it on a sour note. I mean, New York does have better pizza, but I do love deep dish, so.
All right.
It's okay.
Look, I still order from Giordano's, so I actually changed Giordano's location from which I ordered, but it's still Giordano's, so we still can have definitely can have deep dish pizza and guys, and whatever. I'm really looking forward to to actually have a live meetup. So it's, again, for me it was huge, because getting live in new location and do everything. I got too many changes in my life, so I think everybody knows that I switched jobs, I moved, and yeah.
Wow! Congrats.
Thank you. No, that's literally all this year is so many changes. I cannot keep up with my own changes. Yeah, but anyway, so yeah, Jonathan, again, thanks again. And yes, I hope that, next time you will be able to make it live, and for all local folks. So yeah, I will be waiting for you on November 17th. Okay. And I might actually, I did not decide what should be a lottery or something, but actually I have one extra copy of my book. So I kind of want to raffle it. I just did not figure out what should be the topic. But we'll see. All right. Thanks so much.
Thank you. Thank you, everyone.
Thanks. Bye.
Thank you.
Bye.
Bye.
Yes, thank you very much.
Thanks.
Good night.
Bye. Bye.
Thank you.